Hi and welcome back to another Mr. Talk Maths video. This week's problem is the one you can see on the screen right now, and it's about finding the area of this triangle. So obviously, as you can see, it's inside of a quarter circle with 3 points of that triangle on the kind of perimeter. Well, not kind of, on the perimeter. So 1 point is on the circumference, part of the circumference, that quarter circumference, and the other two, as you can see, are on the quarter circle there. And the bottom part splits the radius in half, which might be important, might not be, but equally might be important, might not be. It's a right angled triangle, and we've got two of those in the diagram there, which may or may not be useful. Now, can you find out, like I said, the area of that red triangle? If you want to have a go at the problem, then what I've done is I've labelled the key points, so that's more useful, so you can refer to that in your explanation. I'll just move my head out of the way so you can see the A there. And yeah, if you want to have a go at this, feel free to pause the video now, because I'm going to go through my solution in 3, 2, 1. Right, now the first thing that I did, and most people would probably do, is to work out that this is the square root of 5 here, because we've got a right angled triangle, because you do 1 squared, add 2 squared, and you square root it and you get root 5. That's pretty straightforward. And the next thing I wanted to do is I wanted to label some of these sides, so I labelled these A and B, because these are the sides of the other right angled triangle. And then I got a bit stuck for a little bit. I wasn't really sure where to go with that. I had a few different ideas, tried a few things. But one thing that I definitely wrote down was this: a squared plus b squared must be equal to 5, root 5 squared, Pythagoras again. And the next thing that I did was to draw the radius on, because with circles, anything related to circles, drawing your radii on to key points will more often than not be really useful in solving the problem. Now, the next part was a little bit... not tricky. I mean, I definitely had it on my mind. I was thinking about it. I was thinking about a few other things as well. But one thing that I know is that a right angled triangle, that will lie in a semicircle. So what I decided to do, because I've got two right angled triangles here, both of those, the opposite side to the right angle must be the diameter of a circle. So I drew that circle there. And so I've got two right angled triangles on there. And that's a circle theorem. A right angled triangle lies inside of a semicircle, and the side opposite, like I've just said, the right angle is the diameter of that circle. Now, from there, again, it wasn't apparent immediately, but because I've got these two right angled triangles, what we do have is a cyclic quadrilateral. Now, there is a theorem about cyclic quadrilaterals which you may or may not be aware of, but I'm going to explain it to you now, and it's Ptolemy's, I think I've pronounced that right, Ptolemy's theorem, okay? So this theorem, you've got a cyclic quadrilateral, and you've drawn in, or it has got drawn in, the diagonals from the opposite corners. Now, the next thing, or the key part of this theorem, is about multiplying the diagonals of the cyclic quadrilateral. So if we multiply those diagonals, that is equal to the sum of multiplying the opposite sides. And so, as you can see here, if I multiply AC by BD, the diagonals, that is equal to AB times by the opposite side, so times by CD, add to that AD times by the opposite side, BC. Now, what I've done, just to make that a little bit easier to visualize at least, is I've put it all in colors. So multiply the diagonals, and that's equal to the two green sides multiplied together added to the two blue sides multiplied together. Now, that will always be true for cyclic quadrilaterals, and you can see, hopefully, why that is going to be useful for my cyclic quadrilateral. So if I go back, this is my cyclic quadrilateral here. I've highlighted it with the black lines there, and that's inside the red circle that I drew myself. Now I'm going to use Ptolemy's theorem with this. So I've got obviously my radius, which is one diagonal, and I've got my root 5, which is the other diagonal. So I'm going to multiply those two together, and that is equal to 2 times A, which is the right hand side, times the left hand side, and then the bottom 1 times by B. And so I get, like I've got written down here, 2 times A plus B times 1 is equal to 2 times root 5, the diagonals times together. I'm going to simplify that equation to make it a little bit easier to see and more useful. 2a plus b is equal to 2 root 5. Now at this point, I've got two equations with two variables which I can now solve. So it's just about how we go about solving them. And what I'm going to do first of all is I'm going to rearrange the 2a plus b equals 2 root 5 into b equals 2 root 5 minus 2a. And of course you could rearrange that so you've got a as a subject as well, in terms of b. Either way, it doesn't matter. I'm then going to substitute that equation into the first equation, a squared plus b squared equals 5. Now from there, I'm going to expand the brackets, and I'm going to get a squared plus 20 minus 8 root 5a plus 4a squared is equal to 5. Now from there, I'm going to simplify all of that and get it all onto the left-hand side. And I get this, 5a squared minus 8 root 5 plus 15 is equal to 0, which is a quadratic equation which I can use my calculator or the quadratic formula to solve. So my solutions for a that it gives me, my calculator, are a equals root 5 or a equals 3 root 5 over 5. Now, a can't be equal to root 5 because if we look at the shape, again, the triangle, a must be shorter than the hypotenuse of that red right angle triangle, which is root 5. So it must be smaller than root 5, so it's got to be 3 root 5 over 5, or 3/5 of root 5. Okay, tidying everything up again, I get a is equal to 3 root 5 over 5, collecting that all on the left-hand side of my problem just to give myself a little bit of space. And I'm going to substitute a into either one of these equations, but I'm going to go with the second one again because that's going to make everything just a little bit easier. I don't have to square anything. So I'm going to get 2 times 3 root 5 over 5 plus b is equal to 2 root 5. I'm going to multiply the numerator by 2 and I get 6 root 5 over 5 plus b is equal to 2 root 5. I'm going to subtract that 6 root 5 over 5 from 2 root 5, and I'm going to get b is equal to 4 root 5 over 5. And at this point, we've got basically what we need to get the area of the red triangle. So tidying everything up, I've got a and b. All I need to do now is work out the area of that triangle. Triangle BCE is going to be worked out by a half times by 3 root 5 over 5 times by 4 root 5 over 5, which gives me a final answer of 1.2 units squared. I hope you enjoyed that problem. I hope if you tried it, you were able to get the same answer as me. And if you did like this video and you've watched it this far and seen the solution, please like the video and subscribe because it really helps me out. Thank you for watching, and I will see you next week for another problem solving video. Till then, bye bye.